Hey kids, welcome to Angles and Applications Day 2. So the big idea that we're going to be dealing with today with, as it says, infinity unit conversions. So I need you to keep those two things separate in your head for a second, right? Keep the big idea here separate from the unit conversions because this is annoying, but this is cool. Now, before I start, this concept takes multiple days to get through. It is a challenging conceptual idea, and then the math is actually not that bad, but it gets it's confusing. And the student that says, oh, I get it right away, is not really being honest, in my humble opinion, right? So please have some confidence and some patience as we go through a couple of days with this. This is an HL only topic. This is not for AP. This is for HL math. And for those of you that are really going STEM with your physics, this is also a physics concept. All right, you ready? So concentric circles. So picture concentric circles, and those circles are rotating. And they're connected, right? So they're spinning at the same time, kind of like a record, right? And think about the discs on a record. If you guys are so young, maybe you don't know what a record is. Something called their angular velocities are equal, but their linear velocities are different, right? So take a moment, write that down, highlight what I have, underline the words that I've got in color. And there's a picture. That symbol, Greek letter, is omega. And omega, for some reason, someone chose that to go with angular velocity. So if you have concentric circles, the angular velocity, omega 1, is the same as omega 2. So picture a point traveling along this concentric circle and a point traveling along this concentric circle, and then even the center if you want. If you spin these, if you start these circles spinning around and this point just spins upon itself, right, you are traveling with the same angular speed. And that means per time, you travel through the same angle. So let's say this angle here, right? And let's say in 1 second, this point will have gone all the way over here, here, and of course you can't see where that one is. But in the same time, these particles would have gone through the same angle. Okay. Now, obviously, they are traveling farther if you just took their distance that they traveled and laid it out on a line, right? This particle on the outside of the circle has a much larger arc length than particle 2, and certainly with the point that's spinning upon itself. So I don't know if you can visualize, maybe you've seen ice skaters standing in a straight line, right? And then they start to spin, right? If you have a bunch of ice skaters and their arms are hooked together and they start spinning around, right? This person on the end has to freaking run to keep up, whereas the person in the skater in the middle just kind of, right? Their feet just kind of spin in place. Let me show you a video. So here is a ladybug and a beetle, right? And they are on circles, concentric circles, right? So the concentric circles, they're connected together. And this application has the angular velocity measured in degrees, and I made it 90 degrees. So you can see, hopefully, as they go, right, in 1 second, they've gone about 90 degrees, right? And as I keep going, right, notice that the beetle has a larger arc than the ladybug to travel, but they're traveling through the same angle at the same time. So again, if I pause it there, and then I go 1 second, they both traveled 90 degrees. Right? So that's, I call that, sorry, this is a big C for concentric. Now, non-concentric circles, they are connected, but there's something connecting them. There's like we call it a belt. Think about a rubber band, like when you're working out and you have those you can put those exercise bands around your feet. Particles on these circles have the same linear velocity, but their angular velocities are different. V for velocity. So here the best, the most common example of that is like a bicycle. Right? So you can see here's the belt that connects them. A belt that connects two circles, right? And you have a big circle and you have a small circle. But as this belt turns, right, a particle on the first gear and the particle on the second gear are going to move with the same linear velocity, even though the angle that they spin through is much different. So check this out. Now focus on the red and the green. Right? Can you see they are moving with the same linear velocity? Sorry, my computer's a little glitchy. But you can see that the smaller circle spins, right, almost twice that the orange circle, the bigger circle, spins. But the speed of the two, right, the linear velocity of the red and the green particle are the same. Challenging, I know. I call these B problems for belts. Okay. So on your handout is example 8. So, and I think example 8 is one of the harder ones, so that's why I want to look at that one. So the big idea from the day before, right, is angular velocity, right? We talked about this before. I'm sorry, linear velocity is equal to the radius times omega, right? Our angular velocity. 3 variables. So that really is the only equation that you need, along with some unit conversion, to attack these problems. So I made myself a chart, and I'm going to highlight the information I have. I have a tire that's a 14-inch radius. I have a front gear, call that F, has a radius of 3 inches. And the back gear has a radius of 1.5 inches. If I pedal at 80 revolutions per minute, by the way, a slope value, right? revolutions per minute, right? How many times do you go around per time? Find the angular and linear velocity of the gears and tire. So front gear, back gear, tire. That's why I put these all here. They want front gear, back gear, tire. But they want it in radians per minute, which is also a slope, but with different units. And inches per minute. Everything I have been given so far is in inches. So I think I'm okay with there, right? So angular is in radians per minute, linear is in inches per minute. So let's fill out this table with the information that we have so far. There's my front gear is 3 inches. My back gear is a 1.5 inches. And my tire is the largest at 14 inches. Notice I already filled in the angular velocity that was given to me, which was 80. And I made sure to put the units, revolutions per minute, but I already made note that I need to convert those units because they asked for radians per minute. So look at what I wrote next to that. 2 pi, because in radians, right, to go around a circle, any circle, I don't care what circle you have, to go around a circle is 2 pi times the radius, right? So 2 pi radians per revolution. Why do I like that? Why is that a great unit conversion? Because look what happens when you multiply. I can multiply 80 times 2 pi and I get 160, but look what happens when I multiply these units. By. And I am left with radians per minute. And the nice thing about radians that you have, right, that we learned last year, radians are unitless, right? So that's why our unit circle, remember our unit circle from last year? Whoops. A unit circle, right? We made the radius of the unit circle equal to 1. So the circumference is 2 pi times the radius, but the radius is 1. So the circumference of our unit circle is 2 pi. And I can take any circle and say its radius is 1 unit, right? So I'm using that here. 2 pi, it's a unit circle circumference, 1 time, that's how long it takes, right? The circumference, the arc length, 1 time around the unit circle, radians per revolution. So bam, there's my angular velocity, 160 pi radians per minute. And no, I don't want to round pi, right? This is exact. Pi is an exact value. Now, notice I put a yellow box around front gear and back gear because look at your notes that you just took. What's true about the front gear and back gear? What's true about their angular velocities? I'm sorry, right? This is the belt problem. Their linear velocities are the same, right? That's what you just took in your notes. As long as you have a belt, B is for belt, the linear velocity is the same. So all I have to do is get from the angular velocity to the linear velocity. Gee, I wonder how I could do that. What do I have up here in my equation? Linear velocity is equal to the radius times omega, but I have omega, check. So there I go. The velocity of the front is equal to the radius times omega. And the omega I just found, notice I keep my units with me because what happens, this is really inches over 1, right? So you have inches times radians, but what kind of units are in radians? Unitless. So inches times radians, think of this as a 1, right? It's kind of like a identity per minute, 480 pi inches per minute. That is the linear velocity of the front. So what's true about the linear velocity of the back? Because they are connected by a belt, right? So you have right, a point here. Oops, sorry. Point here on the front gear and a point here on the back gear, right? And as you pedal, the small gear has to turn much faster to keep up with the big gear, and it keeps up because it is connected with a belt, right? And that's why the two particles change at, if you think about like I don't know, a coin or something that you can put on there and visualize spinning on each one of those circles. So I'm doing pretty good with my chart, right? So because I got the linear velocity of the front gear, I've got the linear velocity of the back gear. Now look at the blue box that I put around back gear and tire. Why did I do that? Why did I put a blue box around the back gear and the tire? And then I put a C there. Why? C stands for what? Concentric, right? So what do we know about concentric circles? Their angular velocity is the same. So if I find the angular velocity of the back gear, I've got the angular velocity of the tire. So how do I find the angular velocity of the back gear? Well, I've got a formula, right? So here's my formula. The linear velocity which is what I got from right here, is equal to the radius times omega. And what am I after? Hello, algebra 1. I'm after freaking omega, right? How do I get omega by itself when I have an equation? Linear velocity divided by the radius. Now notice what happens when you do that. Think about your units, right? You're going to get 480 pi over 1.5. You're also going to have inches per minute that went with the 480, but the inches was next to the 1.5. I'll put that over here. So what happens to the inches? The inches cancel out. You're only left with a denominator of minutes and a 1 up here. Guess what I'm going to put there? That's unitless. Hello, radians. Oh, I love you. I love you. Bam. Omega is 320 pi radians per minute. What do I know about the back gear? I mean, what I just found about the back gear, what does that tell me about the tire because they are concentric? So again, this time I'm talking about a particle spinning gear on the back gear and one on the table. There's our ladybug and our beetle, right? The beetle here, this particle has to travel a much longer distance, but because they are concentric circles that are connected, they are going to pass through the same angle per time. So I'm going to just drop that in because it's my blue box. Now what do I only have one thing left to do. Fill out the linear velocity for the tire. I've got omega. I've got the radius. Hello, equation. The velocity of the tire is the radius times the angular velocity in radians per minute. Remember, radians are unitless, so when I multiply my unit, I multiply 14 and 320 pi, and I get 480 pi, and I get inches per minute because the radians are unitless. Wow, congratulations, woohoo! You just did your first angular and linear velocity problem. Okay, so, and this one is the most complicated. Most of the other problems before number 8 are a little bit simpler. They're just asking you for linear or just asking you for velocity. Okay, and don't worry, we will do more of these together. Have a great one.